Okay, so last week we started with the limit. Okay, so when define the limit, we emphasize it's not about the value at A, not about. In particular, it may be not defined. It's about the trend when X approaches A. Okay. Then we give an application of this limit. Okay, this no is just the limit. Is find the derivative. For a given X, this difference, this increment on the Y variable, increment on the X variable, the ratio will be the slope of the lines. Ratio. Okay. So one find the derivative of the function at A. We start with this ratio. For A and X as they close to A, we find the difference in Y variable, difference in the X variable, the quotient give us the slope. Then we let this X moving approach A, the limit of the slope defined as a derivative. As we have emphasized, the limit is not about the value when X equals A, because for this one, X cannot be A. It's about the trend when X approaches A, but not at A. Okay. Equivalent also used for formula when we define the derivative. We use this, we emphasize this increment. So here, this size will be H. So X equals A plus H and H. So this one, so we emphasize, they are equivalent. The only difference is whether we emphasize the point itself or the displacement H.
So when do I use it?
Which one do we pick? So it depends. If we want to find in many cases, so this one is easier to simplify because the denominator is simpler, just one term. So this one has the geometric meaning. The derivative is the limit of the slope. Yes, when H approaches 0, it's the same as, so when H approaches 0, this becomes shorter and shorter, X approaches A. So these two limits, they are the same because X is A plus H. When H goes to 0, X goes to A. Either one, yes. You just, sometimes you try both. I try this one. If it works, okay, we go with this. If it doesn't, we go with this. You can switch back and forth. They have different emphasis. So this one emphasizes the geometric perspective. The derivative is the limit of the slope. Then we use this definition. This is the derivative at one point. What if we let this change? If we let a change, now it becomes a function. We call it the derivative function. So again, in this definition, we emphasize the difference of the values from x to x plus h. Consider the quotient, you take a limit. If we compare these two formulas, they are essentially the same. Because again, what's the difference between the two? We replace each a by x. So we from the derivative at one point to the derivative function. X changes, this changes, we get a function. Third formula, so this one, we compute, we get a number. It's the derivative. This one we compute, we get a function. So for this one, if we substitute x by a, we go back to the previous formula. The difference, because normally we use a for a fixed number. For a given number, it's 1, 2, 3, but it's given. We use x for a varying number, a variable. Essentially the same, but just different perspectives. X is the variable. Okay, and we have a very important formula. If it's, so we recall f x is continuous. Okay, let's try to check with Zichen. Do you remember, or maybe in your language, what the meaning of this is continuous at A?
Like if the limit is the same from the right and left side.
All right, okay. And it equals to F. So this continuous A, so if the limit
may not be enough. Just say left side, the right side same may not be enough.
No. So I stopped her. Yeah, that's not it. I'm going to emphasize. So this simple formula has several implicit requirements. The first requirement is this has to be defined. To see it's continuous at A, the function first has to be defined at A, the first requirement. Second requirement, the limit exists. Limit exists means if this is a here, limit from left side, limit from right side, they both exist and are the same. The third requirement, the limit exists and equals the value. With the three requirements, we claim it is continuous at A. And a very basic but a very useful theorem. Okay. If the derivative exists, or in other words, if it's differentiable at A, it's the same as if f is differentiable. Yeah, so it's the same as in this case, it has a derivative at x. So this limit exists.
What is, so if F, let's say that.
This one, if the derivative exists.
What is,
Okay, so this one, either it exists or it doesn't exist.
like you don't get it.
Yeah, if it doesn't exist, this theorem is not about it. This theorem applies only when it exists. If it doesn't, then this theorem doesn't apply.
And then what is difference?
So this is that like what you just said. Sometimes this is not easy to read. It's a different way to say the derivative exists. The derivative exists. Sometimes we say it's a differentiable at a.
What does that?
It means the derivative exists. So these two statements, they are the same statement as I just repeat.
Yeah, what do you mean differential?
Differentiable. That means the derivative exists.
I know what that means, but I want to know what
Okay, what this word means.
like in this math.
Uh-huh.
What is after? Can you give me an example what F differential?
Okay, maybe I should say in a different order. Let me move this.
I think maybe Sakina has her opinion because differentiable and the limit exists actually are different if it's multiple variable.
Okay.
So her reaction may be right. But
Okay.
for one variable, it's okay. For multi-variable, yeah, she has opinion. Yes.
Okay, so in our case, so at this for function of one variable, f is differentiable at a. Yes. And there's the note different. Oh, late. Did I say this? What do you think?
In that case, for some of them, we are studying math. Yeah, good point. Good point. Thank you.
Okay. So for the moment, in this case, it's very simple. A function of one variable x. For this function, we say it's a differentiable at a if the derivative exists. So this is a definition.
But I just don't know what F is differential. It's like not defined by F of A. I like just what is F differential by A?
Okay, so
how do you know if F is differential?
we check if the derivative exists or not. Okay, so here, if we don't know this, there's no other way to check if it's differentiable or not. Okay, so maybe you want something like a continuous. What a continuous means? You know what this is, so you want to know what a differentiable means. Is that what you want?
Like, yeah. Yeah.
So is okay. Another way. When it's not a differentiable? If we know what's not a differentiable, maybe that helps.
How do you know if it's
not a differentiable? Okay, that's why. Like, let's try one example. The absolute value function. The graph, if we check the graph, something like this, right? So at this point, the derivative doesn't exist and it's not differentiable. Because Uh-huh. At 0 does not exist. Okay, let's take that and we will verify this. Okay, first let me finish the theorem and we're going back to that example. Okay, then f is continuous. Very simple theorem, and the proof is also very quick. So the proof for this one, the product of limits. This one we know is equal to 0 when x goes to a. This one goes to the derivative. So if the derivative exists, this limit must be 0.
Not x.
Because when x approaches a, what's the difference? Okay, so like let's see if we go. Well, we'll use this graph. So when x approaches a, what's the difference? The difference becomes smaller and smaller, right? So it's, the limit will be 0.
Go back. It's not the same derivative.
Okay, so here we want to find the difference of the limits. So to find this limit, what do we know? We know that derivative exists. So we want to manipulate the formula. We make an additional term, then we divide it. So if these two cancel out, we recover this quantity, right?
I mean, like, what are you trying to do?
I want to say so that we want to show this is 0. F A. So now we can see what does this mean? When f derivative of a exists, there are several implicit assumptions when we make this statement. One assumption is fa exists. We don't know what it is, but it's defined.
The first.
Oh no. So normally we cannot. You mean this one?
No, that first one. Find if fa exists.
You mean this?
No. The first derivative definition.
Uh-huh.
To figure out if fa exists.
So this one is about the derivative.
Yeah, and you're saying if fa exists, then f is continuous at a. So I need to check if fa exists.
So you mean this one?
Yeah, you said how do you check it? What I'm just confused as to what are you doing with this whole limit?
With this?
Yeah, what is this whole limit?
Okay, so what we want to prove is continuous.
I thought you proved that if you figure out if fa exists.
That's okay. So it's not. So it's a continuous. First, this exists. Second, the limit exists. Third, they're the same.
Right. So if fa exists, then you know that f is a.
No.
That's what the theorem says.
Okay, if this theorem is about the derivative.
Yeah.
Uh.
if the derivative exists.
Yes.
So can't you just figure out if the derivative exists by using the formula?
So this formula tells us the limit exists. The difference, this, we want to check whether this go to 0.
What does that do? Why are we checking?
If this goes to 0, then this is the same as, let me reformulate. This is the same as limit. I did the same.
Yeah, but technically, can't you also check if f of x is continuous at a by just seeing if the derivative exists? Like you don't need to technically you don't need to do all of that if you just check if the derivative exists.
We could do that.
That's just my question. I just like, can you?
Yeah. So this theorem guarantees you can do that. Okay. So after we prove this, now we can see. Yes. Okay. So is
Because usually my teachers don't do that, so I was just.
okay. Yeah. So here sometimes we will give something, and we say why it's true. So,
Okay, I'll just write proof.
okay. Yeah. So this is the proof of the theorem. Okay. Now we see it's the product of the two parts. This part is 0. It's easy. This part to go to the derivative. So 0 times the derivative. Again, we use another property about the limits. Because both limits exist, so the limit of the product is the product of the limits. Another property of this. Okay, now let's go back to this question. I want to verify this, the derivative does not exist at 0. Okay, so let's start with the definition. Okay, so let's plug in and see how far can we push. So it will be x. Okay, so again, how do you find this limit?
Oh. It just or 0.
So x cannot be 0. So we cannot substitute. So let's check with who's here. Elisa, okay, you arrived. Elisa, what would you do for this limit?
Do like the limit for the positive and the negative.
Okay. So we split this into 2 parts. When x is positive, the absolute value of x, just x. So this will be 1, 1. X is negative. The absolute value is negative x. Simplify. Okay, now we have 2 different one-sided limits. Zicheng, what would you say about this limit?
It doesn't exist.
Because on one side we get a 1, the other side get a -1. So this one, it doesn't exist. Okay, so this is an example where the function is continuous. It is continuous, but it's not differentiable at 0 because this doesn't exist. Okay, so now conclusion, fx.
If F0 doesn't exist, it's not continuous, then F is not continuous.
There's no, so this is a one-way implication. If it exists, then it's continuous.
But if it doesn't exist,
No, there's not the other implication.
no, because F of,
Yeah.
if the derivative doesn't exist,
Hmm.
F is not continuous.
We cannot see that. So this one, the derivative doesn't exist, but
It's
still continuous
F is F.
at 0. So the derivative doesn't exist, but this function, we can see the graph is a V shape, it's continuous. So, so this one is continuous. But the derivative doesn't exist. In other words, it's not differentiable at 0. Because you can see, being differentiable is stronger than being continuous. If it's differentiable, it must be continuous. But if it's only continuous, then maybe or maybe not differentiable. So this is a stronger requirement. Okay, so now I can conclusion. So differentiable implies continuous, but not the other way. Okay, so do you agree with this? If it's differentiable, it must be continuous. But being continuous alone does not guarantee differentiable.
So that wasn't my question. The question was if the derivative doesn't exist, you can't automatically say it's not continuous.
Okay, that's also true. It's not differentiable, does not imply not continuous.
Okay.
Okay, yes, so yes, that's true. So this is one example. It's not differentiable, still continuous. Okay. So that's a theorem. So we have defined a derivative of a function. The derivative itself is a function. It's a function, so we can take a derivative of it again. Let's go to the second derivative. The derivative of derivative. So we introduce a new notation. We put a double prime over there for the second derivative. There are several equivalent ways for this notation. Sometimes we say y equals fx, a function. We use this y prime with y double prime for the second derivative. And we use dy dx for the first derivative. We also use df dx dy dy dx. The second derivative, sometimes we use a short notation for this. I'm sorry, so it should be x. If this is your first time see this second derivative, you may wonder why did we put 2 over d on the numerator, but the 2 over x on the denominator? Okay, let's check. Sophia, what's your argument reasoning for this? Why do we put 2 at different places? Why do we put 2 not here? Why not here? Uh-huh.
We're
Why not this two? Why do we put a different placement for this square?
I'm not sure.
Okay, yes. Think about this. Zichen, what do you think, Zichen? Why do we put 2 here and x2 there?
I don't know.
Okay. So, Elisa, what's your reasoning?
Also don't know.
Okay. So it's a little bit subtle over here. That's how we take a derivative. So on the, let's see. So the reasoning for this is d dx1. So on the numerator, this d will take a derivative, but on the denominator, this dx. This is a whole term. It's not the d and x, but dx. So here we apply d dx, d dx. We apply this twice. So on the numerator, d once, d twice, so it's d squared. Denominator, dx once, dx twice, dx squared. Okay. So now you see, why did we put a square on d? Because d and d. Why dx squared? So here is on the denominator, so you see dx squared is dx squared. We apply this twice. So you see, that's why you have a different placement. It's not this, you mark them wrong. Not this. These are not mathematical formulas, even they are very similar. Because on this dx once, dx twice, this dx is the whole term square. Okay, so with that, we can go a little bit further. This second order derivative, again, is a function. What if we go one step further? Okay, Sakina, what's next? So if we take a derivative of the second derivative, what would we get? Third derivative. Again, there's several different notations. Sometimes we use this. Because there's too many of this, we use F3 over there to indicate by taking the third order derivative. we also use d3f dx3. We use d3y dx3. So here, this is a notation. It means we're taking the derivative 3 times. Why do we put a parenthesis? Because without it, it would be the cubic power. There's some misunderstanding of this. So here we use the parenthesis to emphasize the derivative. Okay, now I'm going to go a little bit further. F100. Okay, Zichen, what's the meaning of this?
Um,
100.
the 100th derivative? Wait, I don't know.
Yes, it is. So the first, just a prime. Second, a double prime, but it's getting a little bit cumbersome. Third, we'll go to 3. 3 prime or number 3. Here, 100 is unimaginable if we put 100 primes.
Mhm.
Sometimes you lost the count, have to start over again. So we use this to simplify our notation. Okay, so maybe let's try something. We'll start with x, a polynomial, x5. What's the first derivative? I will start with Sakina. Not easy. Not easy. Let's try something more manageable. Let's try x cubed. That means x cubed. Let's try that one.
Derivative function.
So this is just so we have this fx. Sometimes we use this notation for the differentiable of x5. So fx prime as the derivative. Okay, so this means we want to find the derivative function of this. Okay, let's try this one. X plus h. First, let's recall this formula. Do you remember this formula? Okay, so let's check with Sophia. Do you remember this formula, Sophia?
X cubed plus 3x squared h plus 3xh squared plus h cubed.
Okay, so with this, want to find the derivative of it. F, the derivative of the cubic function by definition, it will be h equal to 0. H is so here again h. So what do you know about x? We don't know. It's a variable. H again is a variable. It could be 0.1, maybe 0.001. It's gonna not at the moment. No. Okay. So at this moment, just is abstract. Plus h. Okay, so that's the definition of limit. Then we use our formula. So we substitute this x plus h cubed by this. Then we do some cancellation. This one cancel with the first term. What's left is this one over h with 3 squared. Then we take a limit. Elisa, what do you say about this limit?
It's 3x squared.
What happened to the last two terms?
They're 0.
Okay, nice. 3x squared, 0, 0, 3x squared. Okay, so from this one, we conclude the derivative of x cubed is 3x squared. And we have a general formula for this power function. And dx xn. We assume n is an integer, we get n x minus 1. Okay, so this is the formula. For the derivative of this function. So as an example, if n equals to 3, we get a 3x squared.
Oh,
Okay, now let's check if we go back to the x5. Oops, this color. What's the derivative? Okay, so okay, now what's the derivative? Back to the false. Okay, that's the first one. Now let's go again. The second derivative, 5, to be the first derivative of this. Okay, Zichen, what's the derivative of this one? It's 5x false. 4.
Wait. Uh,
Here it's a multiplicative constant. Okay, so it's okay, because the derivative is a linear function. What does this mean? It means if we have 3fx, if we take a derivative of this, it's a 3f derivative. So because of this, we get a 5x4 derivative. Okay, let's maybe can continue from here. What's the derivative of this?
oh wait, I don't know.
Okay, so this one, if we n equal to 4, what do you have?
3.
N equal to 4. So this will be 4x cubed, right?
Mm-hmm.
So I replace this by 4x cubed. So now this goes to 20. Okay, so now summary, what we have done. The derivative of x fifths, just the formula 5x fourth power. And the second derivative, there will be the derivative of the first. Now let's continue to the third derivative. And Sophia, how do you find this third derivative?
You find the third derivative by doing 20 times
Mm-hmm.
3 and then x to the power of 2.
Okay. Okay, now you can see how we take repeated derivatives. We start with this function. We apply the formula once, we get the first derivative. Then we apply this formula again to this, get the second derivative. Apply it one more time, third derivative. Okay, so now if we go a little bit one more step, dx is 4, dx 4, x5. What would you do? We do this one more time. Mm-hmm. Okay, 120x, yes. And Elisa, one more time, last one. Okay, 5.
$120.
Just 120. Okay. Okay, now you can see taking derivatives is not that difficult. You just follow the rules one by one. Okay, let's see. So let's have 4 minutes break and we'll be back at 11. Okay, 4 minutes break. Next, we move to chapter 3 about differentiation rules. How do we take derivatives? The first formula we have learned is the power. N is an integer. In this case, we know the formula is the derivative is n x minus 1. And we also find the derivative of the square root. For this one, we use the definition. Okay, so this is definition. Then we multiply this by the conjugate part to simplify this. Oh, it's not H. Numerator is multiplication of the difference with addition. So we have the formula to be the difference of squares. So this is the limit. this time we can plug in, we get so instead of using the square root, I use the negative power. So now we can compare this derivative with the formula. The formula, so now is x 1/2 derivative is 1/2 so the derivative of the square root is this, and this can be rewritten in this form. Derivative of the square root is simply 1/2 and 1/2 minus 1. It's the same rule we applied for the polynomials. So this formula, initially we say is for integers. Now it also hold for 1/2. And later we will have a more general case. Generalization of this formula. For any real number, the derivative the proof will be given later. So now we just have the formula, not the proved yet. So will be proved later. Okay. Another one, the exponential of x. So as we have mentioned before, we know that the derivative of this at 0, fx equals this. This is the same as so we know the derivative at one point. Now we will use this knowledge to find the derivative at any point. We want to find the derivative function. Okay, so the formula will be the value at x plus h. Okay, just copy the formula, then we substitute. Okay. So we know this limit. How could we find this limit? So Jane, any thought on this one? We compare with this. Well, how could we use this knowledge to find this limit?
Can you factor out e to the power of x?
Okay, so what property did you use to factorize e to the x?
Addition of powers.
Okay, so yes, so one of the laws of exponents, yes. Okay, so we have e to the a plus b, e to the a, e to the b. So we apply this, we get limit 0 e to the x, x, h,
Yeah,
e to the x is a common factor, h minus 1 over h. Okay, now this is fixed. It's a given number. When we take the limit, this part, what we have over there is 1. So the limit of the product will be the product of the limits. This gives us e to the x times 1 e to the x. Okay, so we have our second formula about the exponential function. So e to the x, e to the x. Very useful formula. Now I'm going to ask, I want to take the second derivative. What would you get? Second derivative. Okay, second, now what do you think? So the first derivative is e to the x. If we take a derivative again, okay, let's check. So this will be the derivative of the first derivative. What's the first derivative? Now, the derivative was e to the x. The derivative of e to the x. E to the x. So the first derivative is the same. This implies the second derivative is also the same. I go one step further. Sophia, third derivative.
E to the x.
Again, e to the x. Now go a little bit harder. E to the x. Elisa, 100th derivative
The same.
is the same. Okay, so this is a very special function. All of the derivatives, first, second, third, and up to 100 and even more, they are the same. So we have a very special function, e to the x nth derivative for any int. Okay, a very useful property. Okay, so we mentioned that this natural exponential function is one of the class of exponential functions. In particular, 2 to the x. What's the derivative of this 2 to the x? Okay. So e to the x, how did we find the derivative? We used a very basic property. We know the derivative at 0 is 1. With this knowledge, we found the derivative. So for this one, what's missing is the derivative at 0. If we know the derivative at 0, then we can recover the derivative function. So at the moment, I will give the formula and we'll come back to prove it later. Will be proved later. Okay. So we will take this for granted at the moment. Now I'm going to ask you, Sakina, what's the second derivative? So the second derivative is the derivative of the first derivative. It will be the derivative of the first. What's the first derivative? 2x log 2. Now if you take the derivative of this again, what do you get? So this one is a constant. We can move it out. We get not equal. Now if we take the derivative, what do you get? 2 to the x. So if we want to find this derivative, what do you get? Okay, so this gives us another log 2. So this 2 log 2 is the square. Okay, Zichen, third derivative.
The derivative, so you have to find the derivative of 2 to the power of x and then log 2 squared.
Okay, so this will be the derivative of the second. So second is again, this is the constant, we can move it out. They will give us another log 2. Okay, now 1 and square give us 2 to the x log 2 cube. And Sophia, 2 to the x, I want as 100th derivative. What your answer will be?
It would be 2 to the power of 2 to the
So,
power of x times natural log of 2 to the power of 99.
99 or 100? You can see first derivative logarithm 2, second derivative square, third
Oh, it's
cube.
100.
Yes, it's 100. Okay. Okay, let's find the. Okay, so this is about some basic functions. We found the derivatives. And the next one, you have more complicated functions. How to make things easier? I have some rules we can apply. Product rule and quotient rule. Two important rules we can apply to simplify our calculation for the derivatives. The first rule, product rule. The product of two functions, this fx, gx, the product. Again, this is the function. To find the derivative of this function, we have the following rule. when we take the derivative of the product, okay, so it's the summation of two terms. The first term, we keep the second function unchanged. First function take derivative. Second term, first function unchanged, derivative of the second term. So the product rule ended with a summation. In particular, I want to emphasize not, it's not. The derivative of the product is not the product of the derivative. Let's see why. Let's see a simple example. fx is x fifths, gx equals x third. Let's find the derivative. And their product. Simplify and find the derivative of their product. I will give you a few minutes to finish this. Get a pen and a paper, try to do the calculation. Elisa, first one, derivative of f.
5x to the fourth.
And Zichen, second one. X cubed. What's the derivative of x cubed?
Wait, I'm not sure.
So the formula we had for the power is this. N's power will be n, I will reduce the degree by 1.
Okay,
Uh-huh.
so 3x squared.
Uh-huh, yes. Okay, so it'll be 3x squared. And the Sakina, what's the product of the two functions? Okay, so this will be x. And now what's the derivative of the product? So first, what's the product? It's x to the 8th you just found. What's the derivative of this? X7. Now we are going to compare the summation of this and the product of derivatives. So comparison. Okay, use the formula you have obtained, find the product of the derivatives and the summation of these combinations. So you have the function, yes. Comparison, are they the same thing? Okay, let me check.
So this one is 5x to the fourth times x to the third,
Okay, yes.
5x to the second,
Okay, yeah.
and then g derivative.
What you have is correct. But here, I want to do a little bit further. Here, I claimed it's not this. So I want to justify my claim. So here we have the derivative. We have the derivative. Let's find the product of the derivatives. What do you have? It's product 15. Yeah.
Okay.
Okay, so this will be 5x4 3x squared 15x6. And this will be 5x4 x cubed x5 3x squared. It will be 5 7 3 7 8 7. Okay, so now we can compare this with the result over there and say they are different. So the product rule is not the product of the derivatives. Okay. On the contrary, this looks more complicated, but they have the same answer. So be very careful because this happens very often. The derivative of the product simpler but incorrect. To have a correct formula for the derivative of the product, we have to have the addition as we have over there. First part, second part, then we have this. So it's not this one. Okay. Now let's have another application. Let's find the derivative of the product. x5 e to the x. Apply the product rule, see what you get. Remember, use the correct formula. It's not the product of derivative. For those on Zoom, you can answer your answer in the chat. I'm going to check. Apply the product rule, not the product of derivatives. Okay, I have one from Sophia. Yes, okay, that's correct. Okay. Elisa, you're still working? Are you answering? And it's Chen? What do you have? The product rule. Yes, very good, very good, very good. Always remember to apply the correct formula. Okay, Lichen, are you working on it?
Yeah.
Okay, okay. So when we apply the product rule, there will be the summation of the first derivative, copy the second function, copy the first function. Second, this one. So this one will be fine. E to the x. Okay, so we will stop here. Let me stop recording, and then I will check if you have any questions.